So most of the stuff I'm going to talk about can also be found in the poster. And this is all about data assimilation. So what is data assimilation? Basically, it's a process to combine some prior guesses, which is also referred to as the background or the forecast, with observations to produce an analysis, which in this case is black, in the hope that an analysis is closer to the truth than your initial guess. So in summary, what you're doing if you're doing data assimilation is starting off with the background, then DA, and then you end up with an analysis. Okay? In my work package, we're looking at developing data assimilation for the new SASIP ICE model. And there are several aspects we want to look at. So in this talk, I'm going to talk about how we can exploit features of the numerical core of the new CICE model for data assimilation. The ICE models are very non-linear, and you have non-Gaussian errors, which conflicts with what the data assimilation wants. So in the future, we hope to use machine learning to move from the model output to some latent space in which these requirements are satisfied. And then at the end of the project, hopefully there will still be time to see whether we can use machine learning to divide the error into an error coming from advection and an error from more local processes like melting and freezing. But in this talk, it's just going to be the first one. So data assimilation is very powerful. It's also a massive pain at times. And this is mainly because every problem a modeler can face becomes more harder to deal with if you're doing data assimilation. So if your model is slow, then that's as a modeler you need some patience, but as a data assimilator it becomes really difficult to run your model. If your model is unstable, that is a problem if you're a modeler, but it becomes excruciating if you're trying to do data assimilation, because as a data assimilator you're constantly adding corrections to your model. So to overcome that, we've developed a small 1D CICE model using Firedrake, with the idea that we can run this model faster than the full model, and we can experiment with it, and it's easier to interpret than a full model. Currently, I'm in the process of refactoring and documenting it, but it should see daylight at some point, and then you will be able to find it on the SASIP GitHub. Okay, to show what this model is capable of, these are the equations that are solved by the model. So we got the C thickness is basically, CICE thickness is basically the result of a conservation law. Then we've got momentum, which gives you the acceleration of the sea ice driven by wind forcing, which is in these two terms, as well as some divergence in the stress term, and that stress term on its term is linked to deformation of the ice, that's the spatial gradient in velocity, as well as advection term and dissipation term. Okay, so the wind forcing in this model looks as follows. It's a periodic domain. Then occasionally we get these strong winds, and each ensemble member experiences a Gaussian-shaped wind field that slightly changes, that differs in the height of the Gaussian and basically in the the center point of the Gaussian. The numerical core of the sea ice model uses discontinuous Galerkin. What does it mean? That means that in each grid cell, and two grid cells are shown over here, the solution, which is this dark black line, is approximated as a linear combination of the basis polynomials. Those are the colored polynomials with a certain coefficient. And Weierdrake uses Lagrange polynomials, which are defined, in which the coefficients in front of the polynomials are defined by the value of your solution at a specific set of points. These are the Gauss-Labate points. As we will see later on, Lagrange polynomials are not the only option. Other families of basis functions are available. So what does this look like? What we well, like this. So we're looking at the velocity of the sea ice, the thickness of the sea ice, and the stress in the sea ice as function of the position in space, and for different orders of Lagrange polynomials. The question now becomes, can we leverage the fact that these discontinuous Galerkin solvers resolve the solution within grid cells as a polynomial for our data simulation? And we think we can. So in the current setup, if there's a lot of small-scale signal, which is the black line, then dense observations coming from, for example, from satellites can see that small-scale variability. However, the model, in the current generation at least, can't represent all this small-scale variability. So what is currently being done is super-obbing, which is basically averaging all the observations within blocks, and then assimilating this average as a single observation at different points. So this is a bit of a waste of information that is in the observations. And our question is, with the sub-cell solution being available, can we now assimilate more observations, so do less super-obbing? No. Of course, if you got polynomials, you can take the derivative, and we want to know, is that derivative meaningful in the sense, does it correspond to the actual derivative? And finally, can we use it for something called localization, which is specific to the use of ensembles in data simulation? Okay. In the film, in the animations of sea ice, we saw that there wasn't that much small-scale variability in the model solutions, which is a bit of a pity, because we think it works better if there's a lot of small scales. So instead of using the pi-ice setup, we switched to an artificial setup in which we generate a signal from a certain covariance. Then 41 times we add a perturbation to it coming from another covariance. We keep one of those ensemble members apart, and then apply super-obbing to it to generate artificial observations. And we map the other ensemble members to lower dimensional grids. And this is basically the same as saying, well, a model can't represent all the small scales. We do that in two ways. One way is projecting it on one of these polynomial bases. The other way is just taking the Fourier transform and throwing out all the small scale Fourier coefficients. And the question then is, can we now do successful assimilation using smaller superorbing width or equivalently more observations? And that's shown over here. So what we're looking at is the ratio of the error after data assimilation versus the error before data assimilation. So smaller ratios is better DA performance. For different superorbing width, so smaller superorb width is more observations for different types of models, with the black line being the setup that represents our current generation of model. And what we see is that initially, with our current generation of model, there is some improvement in the performance as the superorb width decreases, but it levels off because the model can't represent those small scales. And if we're using DG schemes, we see that first of all the ratio is lower, and it also keeps decreasing. And this is most visible in the error in the first order derivative. The second order derivative, however, shows ratios around 1, which basically means that the DA doesn't do much. And I think that's because it's just the DA can't separate the noise in the observations from the actual signal in the second order derivative. But it's something that needs to be looked into. The sampling. So these DA schemes need a specification of the error covariance. So that's the covariance between error at different points in the model. And they get that from the ensemble, or they estimate it from the ensemble. And there's a problem with that, because as this graph shows, if you got a true correlation that is 0, then if you make an estimate from an ensemble and you look at what the probability is that you get a certain value, and you see that even if the true correlation is 0, you might have a non-zero probability that you get a non-zero sample correlation. So the way that's dealt with in data assimilation is usually to say, from a certain point, if your sample correlation is smaller than a certain value, you consider your correlation to be 0, and that's a function of space. So basically you say, if the distance between the points becomes large, you taper your correlation to 0. The idea now is that for the smaller scales in your ensemble, this distance over which correlation curves should go to 0 is smaller than for the larger scales. And conveniently, there is a set of basis functions in the discontinuous Galerkin that give you the possibility to split the scales, in the sense that they decompose your solution as a sum of the 0th order, 1st order, 2nd order, etc., etc. And our idea is then to transform the solution to a set of coefficients in front of these polynomials, and then localize each of these coefficients using a different localization scale. So what does it look like? This is the correlation between two points in a very big ensemble. This is the same correlation, but then using a limited set of ensemble members, and as you can see, there are now all kinds of non-zero correlations where they are 0 over here. That's because we're using a limited set ensemble with spurious correlations. And this is what this small ensemble correlation looks like after localization. Over here we mapped the ensemble members from the state space into coefficients in front of the Legendre polynomial. So basically this shows the correlations between the coefficients in front of the zeroth order polynomial in one cell and the zeroth order polynomial in the other cells. This shows the same correlation, but now for the coefficients between the first order polynomials and the first order polynomials in other cells, etc., etc. And clearly, if you look at the width of this correlation, then for the zeroth order polynomials, it's quite equivalent to the width of the whole set of ensemble of your state in state space. But for the higher order coefficients, this width narrows. So it would make sense that if you have to localize this, the smaller ensemble, that you would use a smaller localization radius for the higher order coefficients than for the lower order coefficients. And that's what we've done. And then transformed it back to state space, and it looks like this. And what we see is that this method is somewhat better at representing the low negative correlation that can be seen in the just offside the diagonal, and better match there. But overall, the performance seems to be comparable. So that's something we're gonna look into further. Okay, so the conclusions. If you're using a DG model, or if you're doing DA in a DG model, it is sensible and it is possible to simulate multiple observations per red cell. If you do so, you can correct not only the zeroth order derivative, but also the first order derivative. And it looks like that there is a need for a different correlation, use of different localization scales for different orders, though it is yet to be seen whether that also improves the output of the data assimilation.